Hello, everyone. This is the second part of the lecture on momentum, impulse, and collisions. And in this part, we're going to talk about collisions. So the collisions in physics are called elastic, inelastic, or perfectly inelastic, depending on whether the kinetic energy is conserved or not. In the picture, you can see the golf club hitting the ball and slightly deforming it in the process. So this change of shape or deformation is going to cause some energy losses. Therefore, this collision is going to be called inelastic. The perfectly inelastic collision is the one when the two objects that collide stick together, and they can also change their shapes in the process. Examples of such collisions are two pieces of putty colliding, and they stick together and move with the same velocity. Another example is a meteorite colliding head-on with Earth and burying itself in the surface of Earth. So those are the perfectly inelastic collisions. In the pool, collisions between billiard balls are considered to be almost elastic. So in this case, even though separate or individual momenta and kinetic energy of billiard balls might change as a result of collision, but the total energy and total momentum are conserved. So again, to summarize, we call elastic collisions the ones that conserve both momentum and kinetic energy, and inelastic, only momentum is conserved, but kinetic energy is not. And then as a special case of inelastic collision, we have perfectly inelastic collision. That's the case when the two objects stick together and move as a whole. So let's consider think pair share 3 that talks about a car and a large truck traveling at the same speed, colliding head-on and stick together. Which vehicle undergoes a larger change in magnitude of its momentum? So possible answers are the car, the truck. The change of the magnitude of momentum is same for both, or it's impossible to determine without more information is needed. So to answer this question, we need to first pay careful attention to what it says. It says change in the magnitude of the momentum. And we remember that parts of the system can experience a change in momentum that we call impulse. However, if these two parts of the system undergo a collision, they're experiencing opposite and equal in magnitude force, which leads to opposite and equal in magnitude impulse. So let's go back to the slides that have these equations. Here's the impulse that 2 applies on 1, and it's opposite and equal to the impulse that 1 applies on 2. And also, we're gonna remember that impulse is change in momentum. So if we go back to this question, which vehicle undergoes larger change in momentum? Actually, it's the same, because they both give each other equal and opposite impulse. So let's consider the equations that cover perfectly inelastic collisions. So before the collision, a ball of mass m1 and a ball of mass m2 are having velocities v1 initial and v2 initial, and they move independently. After the collision, they stick together and they have the same velocity. In all of the collisions, momentum is always conserved. but in inelastic collisions, energy is not conserved. We're going to write down momentum conservation before and after the collision, knowing that before the collision, M1 had velocity V1 initial, and M2 had the velocity V2 initial, and after the collision, we're dealing with an object of total mass M1 and plus M2 because they stick together, and that has a velocity VF, V final. To solve this equation, we will find V final as this equation. Let's do a think pair share 4 for an object of mass m that moves to the right with the speed v. So since we're immediately from the first sentence, we can conclude that this is a one-dimensional problem because we have left and right only. This ball collides head-on with an object of mass 3m. So this is a 3 times the mass of the first object that moves with the speed v over 3, so 1/3 of the speed, but in the opposite direction, which means it's moving to the left. If the two objects stick together, what is the speed of the combined object of mass 4m after the collision? Possible answers are 0, half v, v, or 2 times v. So it is a tricky question because you need to use conservation of momentum before and after the collision. So the total momentum of the system is mass times v for the first guy, and it's going to be positive because it's moving to the right. And then I have to add 3 times the mass m. This is the mass of the second object multiplied by, what do you think is going to be the sign of this guy's velocity? Because it's moving in the opposite direction, we're going to have to write negative v over 3. So what do you think this whole expression equals to? It's actually equals 0 because 3 and 3 cancel, and negative mv plus positive mv is going to give us 0. So this is the total momentum of the system before the collision. Okay, and the collision always conserves the momentum, so P initial has to be equal to P final. So the answer is 0. Okay, a skater using very low friction rollerblades, and a friend throws a frisbee at her on the straight line along which she's crossing. She's catching the frisbee and holds it. What type of collision is this? So the person and the frisbee are 2 separate objects. By the end of the interaction, these 2 objects are together. So we're going to say this is a perfectly inelastic collision. Think pressure 6. The skater tries to catch the frisbee, but it bounces off her hands and falls to the ground. What type of collision is this? We cannot say this is perfectly inelastic. However, since it bounces off her hands and falls to the ground, we can say that it's inelastic. Why don't we say that it's elastic? The frisbee is moving and then it does not. So the energy is lost in this collision. Therefore, the collision is not elastic. Okay, think pair share 7. Now the skater catches the frisbee and immediately throws it back with the same speed relative to the ground. So this is the case of elastic collision. I'm sorry. This is, again, a case of inelastic collision. because the skater will lose speed during the collision. And let's go to think pair share 8. In a perfectly inelastic one-dimensional collision between the two objects, what condition alone is necessary so that all of the original energy of the system is gone after the collision? The possible answers are: the objects have momenta with the same magnitude but opposite in direction. As we have seen, this is not guaranteeing that kinetic energy is zero. The object must have the same mass, the object must have the same velocity, and the object must have same speed with velocity vectors up in opposite directions. So the objects must have same magnitude of momentum but in opposite direction. If the initial kinetic energy is transformed, then nothing is moving after the collision. Consequently, the final momentum of the system is necessarily zero because nothing is moving. Because momentum of the system is conserved, the initial momentum of the system must be zero, meaning that the two objects must have equal and opposite momenta before the collision. So let's look more closely into one-dimensional collision for the elastic collision. Let's remember that elastic collision means we have the momentum that's conserved and kinetic energy is conserved. So if before collision, the two objects M1 and M2 have their initial velocity V1 and V2 initial, and after the collision, they're going to have different velocities. Then for those velocities, we can write the conservation of momentum. M1 V1 initial plus M2 V2 initial has to match M1 V1 final plus M2 V2 initial. And their kinetic energies. M1 V1 half M1 V1 initial squared. This is the kinetic energy of the ball number 1 initial plus the kinetic energy of ball number 2 initial has to be the same as the sum of their kinetic energy final. We're going to look at these equations again, and here's these two equations. We rewrote them, and we're gonna rearrange the kinetic energy equation in the following manner. We first cancel 1/2 everywhere because every term has 1/2. And then we are going to move the terms with the mass 1 on one side. So when this guy goes on this other side, it's going to come with the negative sign. And mass 2 to the other side. And similar thing is going to happen to this guy. He's going to gain the minus sign. So rewritten, we now have this. The difference in squares, or the difference of squares, we're going to decompose into product of difference and the sum. It follows from one of the identities that say that a squared minus b squared can be factorized into a plus b times a minus b. I hope you guys have seen this identity sometime before, maybe in high school. So the difference, the change in kinetic energy, okay, this is a negative change in kinetic energy of each ball is equal, which factorizes into this expression. But then we realize that some of these things look similar. because if we rearrange now the momentum conservation, we're going to have so we collect everything with the mass 1 on one side. We're going to get mass 1 factoring out times the difference between V1 initial and V1 final. This happens when we transfer M1, V1 final to the left, equals mass 2 times V2 final minus V2 initial. This happens when we put this term on the right side. It gives the negative sign. And now we see that the same equation, the same terms are present in the equation that we obtained by factorizing the kinetic energy equation. So divide the left side by this left side and this right side by that right side. We're going to get that V1 initial plus V1 final equals V2 initial, V2 final plus V2 initial, which can be rewritten as this last line. I would actually, for clarity, keep it in this original form. So V1 initial plus V1 final equals V2 final plus V2 initial, because we divided this equation by this equation. You can see that if you rearrange the terms that have initials only, you're going to get V1 initial minus V2 initial equals V2 final minus V1 final, which for some reason in the textbook they wrote this way. So what we now have is the problem-solving strategy, because we have different equations that come from different theorems and laws that allows us to write multiple equations. So first, we need to pick a system of coordinates. If it's a one-dimensional coordinate system or problem, that means pick one direction to be positive. Or if it's a two-dimensional problem, then you have to select X and Y axis. Try to draw a diagram that contains parts of the system before and after the collision with their relative momentum, or label their velocity. Then write down the conservation of momentum for the parts of the system before and after the collision. If the system, or if the problem says that the system is perfectly elastic, or the collision was perfectly elastic, you have one more equation at your disposal that is coming from this previous equation. It talks about the connection between final and initial velocities of object number 1 and object number 2. And then using these two equations, solve for whatever the problem is asking you to find. Let's do think pair share number 9 that talks about the bowling ball on the space station that is floating at rest, and somebody nudges a ping pong ball towards it at speed v, initiating a perfectly elastic head-on collision. What's the closest answer to the ping pong ball after the collision? The possible answers are 0, half of v, v itself, 3v, and 2v. So in a one-dimensional collision, the relative speed between the two objects is unchanged. This follows from both conservation of momentum and the conservation of energy. That means after the collision, the relative speed will also be v. And since the bowling ball is not going to move out after the collision with a ping pong ball, the ping pong ball's speed will be closest to v. So the answer is v. Now we're going to consider a special case of perfectly elastic uh, I apologize. We're going to consider a collision between two objects, one of which is at rest, and it's not a head-on collision. So after the collision, the two parts spread from the original direction. We're going to write down X and Y equations for the momentum conservation. Since we don't know if the collision is perfectly elastic, we cannot write down anything about their kinetic energy. But we do know that object 2 was at rest, so V2 is 0. We also know that we can choose a coordinate system in such a way that the x component and the velocity of the first object are in the same direction. So again, V2 initial, both x and y are 0 because object 2 is at rest. And then we can align the coordinate system with the x component of the first object's velocity. In that way, we can say that the y component has 0. There is a 0 in y component for first object. If we mark the scattering angles as theta and phi, then these two equations can be written where initial momentum of the first object, that is going to glance off of mass 2, that's why these collisions are called glancing collisions, it's going to be equal to the final momentum in the x direction, which we will now have to recall how we decompose a vector into x and y components by using trigonometry. If this angle is theta, then the x components will both come with cosine of theta and cosine phi. So you see here is m1 v1 final cosine theta. That's the x component of the first mass momentum. And we add that with the second object's x component final momentum. For the y component, initially we have 0 for both objects. And finally, we have mass 1 times v1 final times sine of theta. But for the second object, we must have negative y component. So there is a typo in the textbook. This minus sign needs to be, this plus sign needs to be replaced with a minus. Where V2 final is the speed of the second object and sine phi is phi is the angle between the x and V2. So using all these equations, we can now try to solve some problems. This problem talks about two identical pucks they're only different by color. One is orange and another is blue, but they have the equal mass. And they're involved in perfectly elastic glancing collision. So again, what is the glancing collision? It's the collision where one part is initially at rest and the collision is not head-on, it's off-center. Because of that, the final momentum will be scattered from the original direction. So now we're having perfectly elastic glancing collision. So it's going to be again the same situation. However, we're given that the collision is perfectly elastic, so the energy is conserved. But we'll see that we don't even need this information. We're given that initial velocity is 3.85 for the orange puck. And after the collision, the orange puck has angle 39 degrees and the blue puck has angle 51 degrees. So we're going to start with rewriting the equations for glancing collisions, except for we know that this is wrong. It has to be the minus sign. Also, we know that both pucks have equal mass, so in these equations, we're gonna have to use m1 equals m2, and let's say set it equal to some m. So in this case, we can write some m times 3.85, right? This is our x component of initial velocity of first puck, plus 0. So whenever I see 0, I'm just going to ignore it and not write it. Equals m times v1 that I don't know, but I need to find it, times cosine of what angle? Let's say v1 is the orange puck. So then we're going to use theta, which is given as 39 degrees. Plus m times v2 that I also don't know, times cosine of phi, which is given as 51 degrees. So cosine of 51. There's m in every term here, so I can cancel it. And I'm going to plug in the numbers. So it's going to be 3.85 equals v1 times 0.78. That's the cosine of 39, plus v2 times 0.63, which is cosine of 51. And then I'm going to work on this second equation where I have 0 equals v1 times sine of 39 is going to be 0.63. And then I have minus v2 times 0.78. By the way, this problem says that when there's an elastic collision, the sum of these two scattering angles has to equal 90. That's falling from conservation of energy. But we're not even going, we're just going to check that 39 plus 51 is indeed 90 degrees. So it is an elastic collision. So we're going to solve second equation for V1 in terms of V2. And we're going to get that V1 equals 1.23 V2. And we're going to substitute this back into first equation and then solve first equation for V2. And I'm going to get that V2 equals 2.42 meters per second. And if we put this back into this equation, it's going to be 2.98 meters per second. So we determine the speed of each puck after the collision by using the equations that were derived from momentum conservation for glancing collisions. Let's look at another problem. We have a car of mass 980 kilograms initially traveling to the intersection with the speed of V car equals 18.3 meters per second. and a 1,500 kilogram pickup that's traveling north, then the two vehicles collide and stick together. After the collision, the wreckage moves at the direction 43 degrees above the x-axis. I guess they picked x-axis as a eastward direction. So we're going to start with saying, first of all, we need to, just for clarity, we need to identify what kind of collision is this. They stick together. That means it's perfectly inelastic. And how do equations look like for a perfectly inelastic? Final momentum can be written as the sum of the two masses times final velocity. And recall that, okay, this time it's a 2D problem. Because of that, I do have to carefully say that velocity is a vector, momentum is a vector, because now I have components. Same with the previous problem. What is the initial? So this is going to be my P final. What is the P initial momentum? It's going to be the sum of two momenta, one of the car and one of the pickup. So it's going to be M1 times V of the car that we're given, plus mass of the pickup times velocity of the pickup initial, which we have no information about. And actually, the problem says determine the initial speed of the truck and the final speed of the wreckage. So we need to find the initial speed of the truck and the final speed of the wreckage, which is this guy. And the initial speed of the truck is, in a way, it's this guy. So we can write mass of the car. It's 980. The initial velocity of the car has only the x component. So I'm going to have to break this equation in x and y. So in x, 980 times 18.3 plus the mass of the pickup truck times, and now I'm going to ask, what's the x component of the pickup truck velocity? So the pickup truck is moving north. So it means it only have y velocity, and the x component of the velocity is 0. So this is going to be 0. I hope you guys can see that. And we have to set that equal to the mass of the two objects combined, which is going to be 980 plus 1,500. Times only the x component of the wreckage velocity. And I'm going to do the same for the y component. 980, but what is the y component of the car's velocity? It's only moving horizontally, or I mean, it's only moving eastward. So no y component. Plus the mass of the truck, which is 1500 mass of the pickup times the velocity that we need to find. And that's going to equal, again, the sum of the two masses times the y component of the wreckage velocity. So these are the two equations that we have. But I want you to notice that first equation, we can solve for VFX. So we're going to find VFX as 980 times 18.3 divided by the sum of 980 and 1500, which gives us 723. But the second equation has both V final, V of the wreckage, the Y component, and the speed that we don't know, the speed of the pickup. But we're given something else. We're given the angle for the V final. So this is the V final angle. And I want you to recall how we connect the X and Y components of a vector if we know the angle. We're going to use the tangent of 43 as a ratio of 43 degrees as a ratio of V final Y over V final X. I hope you remember this formula. And since we know V final X, we can multiply tangent of 43 degrees with 7.23. And then multiply that with 7.23. So the answer is for V final Y is 6.774. All these answers are in meters per second. So from that, we can at least find final velocity of the wreckage. Final speed of the wreckage is going to be the square root of 723 squared plus 6.74 squared. (7.23 squared plus 674 squared. And then we take a square root of that. So the answer is 9.8, 9.9. We can also use the second equation to find the pickup's initial speed. It's going to be 674 times the ratio of 980 plus 1500. Six, seven. So 2.66 is the initial speed of the truck. Okay, this concludes the lecture. Good luck, guys, and till next time.